Assalamualaikum and hello everyone. So we're going to continue with the second subtopic, which is 1.2 collision theory. So our learning objectives for today will be to explain collision theory, define activation energy, and explain transition state theory. Finally, draw energy profile diagram for two types of reactions, which are exothermic reactions and endothermic reaction. Okay, so collision theory. Collision meaning when things hit, okay, atau pelanggaran. It is based on these ideas. Firstly, your molecules of reactants must collide in order to form products. Okay, your reactants, they must collide with each other. Secondly, your products are formed only when effective collisions occur between molecules. So that means that you need to have an effective collision. Okay, so if your collision is ineffective, then you will not be forming any products. Alright, so those are the two ideas for collision theory. So what is effective collision? Okay, how do we get a successful collision so that we get our products? Okay, it will only happen under these following conditions, where the colliding molecules must have a kinetic energy equal to or greater than, okay, this sign, than the activation energy EA. Okay, so that is the minimum energy required in order to have an effective collision. Another thing is that your collisions occur at the correct orientation. What does it mean by correct orientation? Correct orientation means the right position. Okay, there must be a certain position, so you will get an effective collision. So you must have these two to get your effective collision. Okay, so let's look at activation energy. What is it really? Okay, it is activation energy. So this is the amount of energy required to activate your chemical reaction or initiate your chemical reaction. It will trigger your chemical reaction. Okay, so activation energy EA may be gained through collisions of molecules, and that energy will be used to break bonds between reactant particles. Then these atoms will form new bonds in the product. Alright, so let's say right here you have your two reactants. So when these two reactants they collide with each other, then you will get a surge of energy. Maksudnya awak punya energy akan makin tinggi, and that increase in energy, that extra energy will be used to break the bond between your reactants. Alright, so this reactant will break its bond so that a new bond can be formed between these two. Okay, then you will get your product. Alright, so minimum energy required is right here. This is EA, the activation energy. Okay, so your reactants must gain energy up till here at least, okay, in order to form products. If it only gains energy up till here, then it will not form any product. Okay, you have not reached your activation energy. If it is more than the activation energy, then you might be able to form the product. Okay. Okay, so next is the orientation of collisions. Orientation maksudnya the relative position for your collisions. So correct orientation means the collision of molecules occur at the correct angle that favors the formation of your products. Okay, for example, let's say we have hydrogen iodide molecules. Okay, so these two molecules will collide, okay, to form iodine gas and hydrogen gas. Okay, so on the top part here is a scenario where you get effective collision, so your reaction will occur. Okay, why? Because your hydrogen iodide, it is positioned in this way, where your hydrogens are, let's say, at the top and your iodine is at the bottom, so that when they collide with each other, you will form your hydrogen gas and iodine gas molecules. Okay, so right here your reaction occurs. This is an effective collision because your molecules are colliding at the correct angle. Let's say if your molecules are positioned this way, where your hydrogen is out here and the other hydrogen is down here. Okay, so opposite, right? So when, not opposite with each other, okay? So when these two molecules collide, your reactant collide at the wrong orientation, okay, no reaction occurs. See? No reaction occurs. You get back your reactant. You do not get your product. Okay, that is what is meant by orientation. Okay, so on your right here is kind of the same examples lah. Okay, right. So next, we know that our reactant will turn to product when it has a certain amount of energy, right? Okay, but actually before your reactant turns into product, you will have a transition state. Okay, a transition state is like a hill. Okay, so this is where transition theory comes in. So this theory, it explains the activation energy EA as the energy required by the reactant molecules to form the activated complex. Okay, your activated complex, it is a species formed at your transition state. Okay, so maksudnya transition theory ni just bagi tahu yang why you need, how does activation energy work, so your reactant molecules will form activated complex. So we're going to talk about activated complex. So what is activated complex? Okay, it is a temporary species formed by the reactant molecules. Okay, they form activated complex as a result of the collision before they form the products. Okay, so why is this activated complex a temporary species? Because okay, it has a short half-life. Maksudnya dia exists at a very short time. Okay, it almost does not exist, tapi dia exist lah, dia ada. Okay, it is the activated complex. It is formed at the transition state energy. This one is the transition state. It is up that hill. So let's say this is your reactant, bawah ni awak punya product. Okay, so this hill, okay, is called the transition state. This is where your activated complex is formed. Okay, so to get more understanding on this transition theory, we're going to look at energy profile diagram. Okay, so on the next slide we will look at how a typical energy profile diagram looks like. So energy profile meaning we have potential energy or just energy in kilojoule or joule, okay, as your y-axis, and on your x-axis you have your reaction progressing from your reactant to activated complex or transition state to your product. Okay, so this is a typical energy profile diagram. So we have our reactants, we have our product, we have our activation energy, the arrow denoting the activation energy, and up here this is the hill, the top, the maximum amount of energy called transition state. Okay, so your activated complex ni, it has the highest amount of energy. Okay, so first you have your reactants. Okay, so before your reactant can become a product, it must gain a certain amount of energy. Okay, at least this EA, right? So it has to gain energy when they collide, and then up here it reaches the transition state. So right here it will form your activated complex. Okay, so this activated complex has highest amount of energy, so therefore it is very unstable. So if it is unstable, meaning, okay, it is very reactive, right? So it will either break a bond or and form a new bond. Okay, depends. All right, so this activated complex, okay, will determine whether your product will form or not. Okay, so your reactant will form your activated complex, and then up here it is like fight or flight, okay, whether or not your activated complex will become product. Kalau dia become product, dia akan jadi product. If not, dia dari reactant dia jadi activated complex, and then it will go back to becoming a reactant. Okay, okay, so that is your activated complex. So how does it look like? So let's say we have methyl iodide reacting with hydroxide ion. Okay, these are your reactants. Your products will be methanol and iodide ion. Okay, so before your products are formed, okay, you have your transition state up here, the hill, and at your transition state you form your activated complex. Okay, so for these reactants, your activated complex is actually this CH3, and you have I, and you also have OH at the same time. Alright, so maksudnya this reactant collides with this reactant and then forms this activated complex up there. Okay, right here we can see that, okay, we have the carbon iodine bond, okay, and carbon oxygen bond. Okay, so these two bonds, okay, in this activated complex are loose bonds. Okay, so right now the activation energy is needed to stretch and deform bond in order to reach transition state. So tadi awak reach activation energy tu, okay, is actually to to break this bond. Okay, okay, so in this transition state we have two loose bonds. Okay, this is your original bond in here, and then you already collide and you are forming this bond. So during this time, okay, your activated complex will either form product or not. Okay, dia akan lose either of the bonds. Alright, so supposedly to form product, your activated complex will break this bond and then form this bond in order to form methanol. Okay, so the energy profile diagram for that reaction will look like this, where we have our reactants methyl iodide and hydroxide ion, and that it will gain energy during collision, and then it will reach its activation energy. So once it reaches its activation energy, it will form the activated complex. So this activated complex at the transition state, okay, you will have two loose bonds, right? One is forming, one is breaking. So in order to form your product, if we form our product, then our carbon oxygen bond will form, while carbon iodine bond will break. Okay, so let's say if your reaction decides to progress, okay, then you will go down and form your product, methanol and iodide ion. So in that process, you will be releasing energy. You will release heat. Okay, so your delta H will be negative. How do you know that? You will know that because your reactants, your enthalpy of reactants will be higher than the enthalpy of your products. Okay, so your delta H is HP minus H reactants. So since this is smaller than this, therefore you will get your negative value, denoting that energy is released when forming methanol and iodide ion products in this reaction. Okay, alright, so that's your typical energy profile diagram with its activated complex. Right, so now we're going to get to know the two types of reactions that we have and how you need to know how to draw their energy profile diagram. Okay, so let's say we have this general reaction. Okay, if your reaction is an exothermic reaction, maksudnya your reaction, this forward reaction will release heat, so delta H is negative. Okay, so look at this left energy profile diagram. We have our reactants right here and our products right here. Alright, and your enthalpy of reactants will be higher than the enthalpy of products. That means when this minus this, you will get a negative value. Okay, so this is your activation energy when your reactants gain energy and form the activated complex. So this is your activation energy, the amount of the minimum amount of energy required for a forward reaction. Let's see, from this to this is delta H negative. Okay, forward reaction maksudnya these are your reactants, these are your products. Alright, so from there to form products, you will lose energy. Okay, release energy. Okay, so another way to know whether your reaction is exothermic is that I would like to tell my students to draw a line for your reactant and your products, and then you draw the arrow from reactant to product. So the direction will be downwards. That means that energy is released. Okay, alright, so that means your reaction is exothermic reaction lah. Alright, okay, so next we have the endothermic reaction. Endothermic maksudnya this reaction, the forward reaction. Okay, let's see here. For this reaction is a positive enthalpy change. That means heat is absorbed in order to form these products. Okay, so let's say now these sama je awak punya reactant and this is your product, but the position, okay, berbeza. So sekarang awak punya enthalpy for reactant is lower than enthalpy for your product. So that means when calculating the delta H, your H P minus HR, you will get a positive value. Alright, another thing is if you draw your arrow, okay, daripada reactant, this is your reactant, this is your product, right? The arrow will be from downwards to down to up. Okay, so this means energy is absorbed, so delta H is positive. Okay, kalau tadi ni energy release, arrow turun bawah daripada reactant to product, tapi ini endothermic, ni your reactant, ini your product. Daripada reactant to product, you naik atas, maksudnya it is endothermic, positive. Okay, so if you look juga dekat your activation energy for your forward reaction, okay, macam biasa dari reactant to product, you will need to gain this minimum amount of energy, right? This is your EA. Okay, this stretch here, right, to form your products. For the reverse reaction maksudnya where your daripada awak punya C and D reactants to form A and B products, okay, the activation energy will be this one, right? Sebab awak kena, you need to gain this minimum amount of energy. So this is the reverse activation energy. Alright? So basically, if you want to find the the reverse activation energy for endothermic reaction, okay, your forward activation energy will be higher than your reverse activation energy. And if you know your delta H, then you can just take this value, tolak with this value, okay, modulus the value saja to get your activation energy. Alright? Kalau macam ni, okay, macam ni, for exothermic reaction ni, awak punya reverse EA, okay, will be from here to here kan. So maksudnya awak punya reverse EA this stretch. Okay, so your reverse EA will be equal to EA forward plus modulus delta H. Betul tak? Okay. Alright, so it's basically the scale for reading your energy profile diagram lah. Okay, so let's say for this example, okay, a key reaction in the upper atmosphere is ozone gas reacting with oxygen atom gas to form oxygen gas molecule. Okay, so the EA forward is 19 kilojoules and delta H for reaction is minus 392 kilojoules. So draw a reaction energy diagram and calculate EA for the reverse reaction. Okay, so first things first, what you need to know is, it already told you the delta H. That means here you have a negative denoting that it is an exothermic reaction. So for exothermic reaction, maksudnya your delta H will be negative, right? It is negative. Why? Because delta H is HP minus HR. So kalau dia negatif, maksudnya awak punya enthalpy for product is lower than for reactant lah. Okay, so minus akan dapat negative. That means your product punya enthalpy will be lower kat bawah and your reactant punya enthalpy energy will be higher. Okay, ni kat atas, ni kat bawah, right? So that is the first thing you need to extract from knowing the type of reaction. Kalau dia exothermic reaction macam ni. Okay, so then you already know the activation energy for the forward reaction, right? For this exothermic reaction, that means that you will need to draw your hill lah. Okay, your hill. Okay, your reactant must gain this minimum amount of energy, your EA forward, 19 kilojoules. Okay, and then form your activated complex, and then it will go down, lose energy to form your products. Okay, alright, so make sure to have your, obviously your labels, y-axis and x-axis, your reactants, your products, your activated complex, your activation energy, and your delta H. Okay, delta H. So this one, your arrow will be, for delta H, will be going down because you are releasing energy. Okay, in exothermic reaction. So that is your energy profile diagram. And then they ask you to calculate the activation energy for reverse reaction. So for reverse reaction, maksudnya daripada oxygen gas molecule to these products. So maksudnya terbaliklah, dari sini pergi sini. Okay, so what is the minimum energy required? Okay, dari sini to activated complex, it will be this. Okay, this is your EA for reverse reaction. Alright, so how do you get 411 kilojoule? So basically you are just adding 19 kilojoule with 392 kilojoule. Alright, okay, I think you can understand that. So we have finished 1.2 collision theory. Make sure to make overview notes based on the learning objectives. I might be calling out any one of your names. And then attempt tutorial question number 9. Okay, alright, that's all. Thank you.